All right. Welcome to RISE Learning Machines seminars, everybody. RISE is Sweden's research institute with nearly 3,000 researchers working all over Sweden on research areas spanning from bioeconomy to material science, transport, and digital systems. Our weekly Learning Machines seminars are organized as part of our Center for Applied AI Research, which brings together researchers working on topics such as natural language processing and machine learning for applications such as environmental modeling and industrial applications. So today, I have the pleasure to introduce Neil Zeghidour, who's a research scientist at Google Brain, a teacher at ENS in Paris. He got his PhD in machine learning from ENS and while working at Facebook AI Research. He's working on integrating signal processing and deep learning into fully learnable architectures for audio understanding and generation. And he's been working on speech separation, speech recognition on raw waveform data, and very recently on language models for audio generation. Today's talk, however, is about end-to-end neural audio codecs. And I will remind everybody that the presentation will be recorded. So if anybody wants to be removed from this recording, just let us know. And with that said, please, Neil, the floor is yours.
Thanks, Olaf. Let's hope that it works again.
It looks good.
Okay, so yeah, so today I'm going to present some work I worked on last year. It's called SoundStream. It's an end-to-end neural audio codec, and at the very end, I will add very recent content from a paper that was actually published in Archive today morning. So first of all, I want to emphasize that it's teamwork with my colleagues in Google, Ahmed Omran, Alex Loebs, Jan Skoglund, and Marco Tagliasecchi. So the goal of this work is to design an audio codec. So an audio codec, it's something like MP3 or Opus that you are likely using on a daily basis. Even if you don't use it explicitly, it's used whenever one needs to transmit audio. Basically, when you stream a YouTube video or you do a video conference like this one on Zoom or Google Meet. The idea is that you record an audio and it needs to be compressed and sent to the receiver, which can decompress the audio and listen to it. So there are several expectations for an audio codec. First of all, it must be fast. So for example, for the case of video conference, you need to be able to have a real-time codec, so that there is no delay between the speed that you produce and its reception by your interlocutor. It must be efficient in the sense that you want to be able to compress audio on a very limited number of bits so that you don't use too much bandwidth. And finally, it needs to be scalable. So what it means for a codec to be scalable is that if, let's say, during this meeting, my connection gets worse, Opus, which is likely currently being used, Opus is going to be able to degrade the quality by reducing the bitrate so that I can keep speaking at a lower quality, but at least you can still receive what I'm saying. So this scalability component is very important for practical utilizations. So since it's a machine learning seminar, you can imagine that there will be machine learning involved in the design of the SoundStream codec. And the question then is, why should we learn a neural codec instead of handcrafting a neural codec? So what you see on the left is a diagram of the encoder of Opus, which we can call a traditional codec. In that case, you have a diagram of different computational blocks that are going to compute each one an operation that was hard-coded by experts. So, for example, in that case, you're going to have voice activity detection, high-pass filter, pitch analysis, and so on. And in that case, each of these operations has been designed based on expertise of psychoacoustics, so the way human perceive sound, so that we can compress the audio without degrading the perceived quality. All of this requires a lot, of course, of expertise and a lot of involvement in the design of the specific filters and operators that are used. What you see on the right leverages, in a way, another type of expertise. So our goal is rather to train a neural network, so a model that makes much less precise assumptions on the type of operations it can learn, right? So it's much less precise than doing pitch analysis and VAD. We have kind of a large class of functions that can be learned by it, but we want to be able to train it to reconstruct audio data while being compressed on a limited number of bits, like we will do, for example, with Opus. So what can we expect to gain from that is that if you look at an expert codec like Opus, it works well and is very fast, and that's why it's used virtually everywhere in production, but it requires years of development. And again, so it's very costly in terms of expertise and iterations to design it. It's not guaranteed to be optimal because, for example, as I said, you're going to create filters and operations in an handcrafted way, right? So you're going to find configurations that work well, but the way it's explored is mostly by human iterations of improving the model. So there is no guarantee that you reach an optimal solution. Finally, again, since it's not learned, but rather handcrafted, it does not leverage the massive amounts of data that we have now. To give you an idea of the contrast with SoundStream, instead of years, it was a few months of development. And actually, after 5 or 6 weeks, we already had a quite convincing demos that then we improved. It can leverage the massive amounts of audio data that we have available. Another interesting thing is that since it's a trained system, if you want to bias your system towards a specific kind of data, it's pretty easy, right? So if you train your SoundStream model on a speech data set, you're going to have a speech codec. If you train it on music, you're going to have a music codec. If you train on a mixture of music and speech, you have kind of a universal codec. So this is very different from, let's say you have an Opus codec and you want it to be very good on a specific type of audio signal, let's say in Spanish speech, at the cost of being worse on other ones. It will be very hard to find the proper adjustments to perform on the Opus codec to reach this kind of biases. While with SoundStream, you can just train it on Spanish speech and it's going to be excellent for Spanish speech. Another, I think, advantage that is not really realized right now, but is more prospective, is that there is currently a trend of developing specific hardware for neural networks. So, for example, the advantage of most traditional codecs is that they use digital signal processing operations that can benefit from dedicated hardware, let's say on smartphones or smart devices and so on. Now we start to see that for neural networks. And so we can imagine that in the future that there will be specific hardware on all our devices that will make neural networks even more competitive with signal processing approaches. So what is SoundStream? To summarize, it's an end-to-end neural audio codec that outperforms state-of-the-art codecs Opus and EVS on speech, whether it's clean, noisy, or even reverberant, and on music using up to 4 times fewer bits. It is scalable. As I explained in the beginning, it means that a single model can serve all bit rates, and that's the first time that a neural codec can achieve scalability. It runs real-time on a single smartphone CPU, and as a plus, it also allows for controllable denoising that you can activate and deactivate whenever you want. So to explain how SoundStream works, I'm going to first break down the way a neural codec works in different steps. So the first one is encoding. So you are provided an audio waveform that you want to transmit to a receiver. The first step is an encoder. So if you are familiar with autoencoders, it's basically a neural network that takes a highly dimensional input and is going to map it to a lower dimensional embedding space. So you have mapped a big waveform to a small embedding space. However, your embedding space is still continuous, right? So it can be technically represented by an almost infinite number of values. Since you want to transmit a limited number of bits, you need to compress the representation in this embedding space. So that operation is called quantization. And the quantized coefficients are what are the compressed codes, and they are what you're going to send over the network. Your receiver has kind of the symmetric model to the encoder, so they have the decoder, and what they receive is the quantized embeddings, and they can dequantize it and reconstruct audio from it using the decoder. So that's the 3 steps. So to give you some background of what was used inside Google before SoundStream, it's a codec called Lyra that is used in Google Duo, so for phone calls. And the way it works is that the encoder is a simple spectrogram, so it's not a learned transformation. It's just a time frequency representation of speech. The quantizer is called a product quantizer, and the part that is learned from the data is mostly the decoder. So it's a wave RNN, so it's an auto-regressive recurrent neural network that takes the quantized embeddings and reconstructs the waveform value by value. So in that case, the solution that pre-existed to SoundStream is kind of a hybrid between fixed signal processing, which is the spectrogram, and machine learning, which is the decoder part, which is trained on datasets. The difference is that SoundStream is going to train everything end-to-end. So in the context of SoundStream, we are going to backpropagate a certain loss that I will describe later in the talk through the entire process, which means the encoder, the quantizer, and the decoder are going to be trained jointly and optimized for the data that we want to compress. So I will go quickly over the encoder decoder because I honestly think it's not really the most important thing, even though it's very important for performance. It's not the most original part of the model. So it's a convolutional network with residual connection. So if you are familiar with residual networks, it's kind of a ResNet. An important feature of this model is that it's causal. What it means is that it does not need to look into the future, which is very important because if you want your model to run in real time, it must be able to send packets of audio as soon as it has listened to them. If, let's say, you had a model which was not causal with a very large context, both in the past and in the future, it means that you will need to wait for a lot of samples to be able to send the current frame. So our model is causal, which means that computing the activation at a certain point in time only depends in the past. An important feature is that we double the number of feature maps every time we stride the model, which is very important for performance. And we have a symmetry, as I said before, between the encoder and the decoder. So the decoder can really be seen as the symmetrical to the encoder. So what is more important here and is kind of one of the main contributions of SoundStream is the way we are going to compress the embedding. So we suppose now we have the encoder that is producing this continuously valued embeddings that you see here in blue from an audio waveform. And let's say, for the sake of the example, that it produces one embedding for 100 milliseconds of audio. A vector of length 3 encoded in flow 16 is going to use 48 bits, right? Since we have 10 embeddings per second, and each embedding is represented by 48 bits, we are running before quantization at a bitrate of 480 bits per second. What we're going to do with vector quantization, and that's the operation that is going to actually compress the data, is that instead of transmitting the blue vector that you see on the left, which is the actual true vector that represents the input data, we are going to have a dictionary, a finite dictionary of template vectors that are called code words. So that's the one you see on the right. And what we're going to do is that we are going to compute the distance between the embedding we want to transmit and all the code words in the dictionary. And we are going to replace the embedding by its nearest neighbor in the dictionary. So in a way, the way it works is that basically you have a dictionary of template vectors, and when you want to transmit a vector, you rather transmit its nearest neighbor among the ones in the dictionary. The reason why you do so is that you can see that to each code word in the dictionary, we associated an index, right? In that case, it's coded on 2 bits. So since the receiver also possesses the same dictionary, instead of transmitting this long embedding with 3 floats, I can just transmit 2 bits, which say which code word the receiver should use to represent the input embedding. So now we only use to transfer 2 bits, which means that if we transmit 2 bits per embedding, and as I said, so the receiver is going also possesses the dictionary, so they receive the 2 bits and they dequantize it to get the code word that corresponds in the dictionary. They pass it to the SoundStream decoder and they reconstruct an audio waveform. What is important is that since we replace an embedding by a code word that is kind of similar but not exactly the same, there is no guarantee that we transmit the exact information we wanted. So it's called lossy compression. So the decompressed data is not exactly the original one we wanted to transmit, but we can consider that it's a good approximation. For example, while I'm speaking right now, what you hear is not exactly the waveform that I produced, but it's as intelligible and pretty close such that it doesn't make a big difference. What is interesting now is that before we transmitted 480 bits, now if we have 10 embeddings per second and for each embedding we only need to transmit 2, now we only transmit 20 bits, which is a huge reduction compared to 480. So this brief introduction to vector quantization I think, allows demonstrating how quantization can drastically reduce the bitrate compared to if we wouldn't compress the embeddings. So that's for simple vector quantization, and it was pretty useful in the toy example that I showed before, but it was really a toy example because now we are going to talk about the actual numbers that we're playing with when we talk about audio compression, in particular over video conference. So in our case, our encoder outputs 75 embeddings per second of audio. So we have one embedding every 13 milliseconds. And what is considered an already very low bit rate for speech communication is 3000 bits per second. What it means is that if we have 3000 bits per second and 75 embeddings per second, we have a budget of 40 bits to encode each embedding. 40 bits to encode each embedding, it will mean that we will need a dictionary that has more than 1 trillion code words inside of it, which is completely impossible. So what it means is that vector quantization cannot scale to even very low bitrate, such as 3000 bps. So you can even forget high bitrate like is used for music, like 320 kbps or even 128 kbps. So even at 3 kbps, it's already impossible to do with vector quantization. So what we're going to rather use is called residual vector quantization. So we didn't invent residual vector quantization. It has existed for decades. What we proposed is integrating it into a deep learning framework, which was not done before. So the way residual vector quantization works is that it's basically a set of vector quantizers. So the vector quantization process I previously shown, we are going to do it several times. So the way it works is that we apply a first vector quantizer, which is called Q1. It gives us an approximation of the original embedding based on the nearest code word in the first dictionary. And we compute the difference between the original embedding and its approximation. So now we have a residual that is much lower in amplitude than the original one. So it's really like just a kind of approximation error. And we are going to quantize this approximation error a second time. And we do that in a cascaded way until we reach the number of quantizers that we are using. To give you an example of how it allows scaling the bitrate, is now, let's say we have 4 residual quantizers. Now, instead of using 40 bits with a single vector quantizer, we split it uniformly across the 4 ones. So now there is 10 bits per quantizer, which means that we only need 1024 code words for quantizer. And since we have 4, basically we have 4000 code words. So 4000 code words instead of a trillion of code words before. So you can see how residual quantization allows scaling in a very, very significant way the kind of bitrate that we can target. Because now we can easily go to 20, 50, even 100 kbps. So as I will show in the experiments, the optimal solution would actually be the one that is not tractable. So in terms of approximation error, the best will be to have a single quantizer with a gigantic dictionary with 10 to the power 12 code words. The more we use quantizers with smaller code words, the more approximation error we're going to do. But as I will show in the experiments, in practice, it's not that much. So it's something that we can totally afford in terms of error. So here you just have basically the algorithm for how it works, but I'd rather point you to the paper if you want to see the details of the computation. So now I'm going to play a video which I think will require that I'm muted. So I will first explain what you will see in the video. What we did in this small experiment and motivated the second part of the paper is that we trained a model with 24 quantizers, right? So it was a residual quantizers with 24 levels. And even though the model was always trained with 24 quantizers, at inference, what we do is that we remove some of them. The idea behind this experiment is that we just wanted to know whether, let's say, I remove half of the quantizers and I feed a partial embedding to the decoder. Is it going to reconstruct something that sounds kind of okay, but just a bit worse than what it will reconstruct with all quantizers, or is it going to completely fail? Basically, we wanted to evaluate the robustness of the decoder to the actual number of quantizers that it received as input. So I'm going to mute myself just to play the video. And by the way, Olaf, if you don't hear the video, please tell me so that I try again.
Sure, yes.
With the exception of the crown. 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 With the exception of the crown.
We heard it.
Thanks. So what you could see is that the more quantizer we add, the more details are added to the model. And what is interesting is that, again, it's very important. This model was trained with 24 quantizers all along. So when at inference, I remove some of them, it's really like an out-of-domain condition for the model, right? And so even for us, it was very impressive and kind of unexpected that it would degrade in such a graceful manner, right? So what it motivated us to do is that since training with 24 quantizers and removing some of them at inference already works, we could even train in these conditions. So training in a way where we vary the number of quantizers, because we definitely have a model that can, in a way, be scalable, right? Because I can choose to remove some quantizers, which reduces the bitrate, and is going to reduce the quality. So if I'm in a context where there is a bad network condition, and I have 24 quantizers, I will just send 12 of them or 6 of them, and so I reduce by a factor of 2 or by a factor of 4 the bitrate, and at a certain price of quality, but it's still intelligible. So what it led to is a technique that we call quantizer dropout. And basically, the idea is that what we did before in inference, now we are going to do in training. So during training, let's say we have n quantizers. We sample uniformly for each batch and each example in the batch, actually, k, a number k between 1 and n. So we keep at least one quantizer, obviously. Otherwise, we will just transmit silence between 1 and n. And so we sample that uniformly for every example, which means that the model is trained to be robust to the variation of the number of quantizers. And at inference, as I said, we get scalability because we can choose to only send some of the quantizer instead of all of them. What you see on the right is it's a metric called vscale. So it's basically a computational proxy for human judgment of quality. So the lower the worse quality, the higher is the better quality. The top line that we want to match or outperform here is the circles. So it's bitrate specific, which means that for the circles, we have a different model trained for each bitrate. So one at 3, 6, 9, and so on and so forth. So 6 different models. Then there is the model that I showed in the video. That's the triangle. So this model was trained at 18 with 18 quantizers. But at inference, we decide to remove some of them. And obviously, as I said, it's kind of out of domain inference. So you can see that the further you go from 18, so going to 9 and then 6 and 3, and the more there is a gap between a bitrate specific model that was trained specifically for this bitrate and the model that is of which I remove some of quantizers at inference. Now the square is the model that is trained with quantizer dropout. And you can see that the model, so again, it's a single model, unlike the bitrate specific, which is 6 different models. But this single model, it performs on par and in a way, surprisingly, sometimes better than the bitrate specific model. So with a single model, we can perform as well as a lot of models for different bitrates. The reason why it's very important is that it's important to understand that if we were to use a codec that is not scalable in production, it means that you need to have a separate model for each bitrate and switch between them all the time, which means a lot of storage that is used to store all the different models. You need to have this switching ability where you're going to load a model instead of another one and so on. So having a single scalable model, it's much more convenient. So now I want to talk a bit about the training objective. So basically, SoundStream is kind of a generative adversarial network, which means that it has 2 objectives. The first one is reconstructing the original audio using mean absolute error or mean square error. So very simple reconstruction loss. The second loss is based on a discriminator. So we train a second neural network called a discriminator, which needs to tell whether an audio that it receives has been compressed by SoundStream or is an original uncompressed audio, right? And SoundStream is trained to fool this discriminator And by if SoundStream reaches its objective, it means that it's able to generate compressed audio that sounds as good as uncompressed audio. So it's a very good objective to use to train the model. And the way we perform compression is simply that we don't add an additional loss that is going to force SoundStream to compress. We basically put the quantization in the middle of the network. So SoundStream has no choice than compressing the coefficients, right? So the embeddings are necessarily compressed. And SoundStream is going to learn the optimal dictionary that maximizes the reconstruction quality despite being constrained to, let's say, run at 3 kbps or 6 kbps or 12 kbps. For evaluation, we use Vscol mostly for development, which we found very useful because it's automatic, right? So it's cheap to compute. You can compute it on your parameter sweeps and so on. I said it's a proxy for mean opinion score, so 1 being very bad and 5 being perfect. The real evaluation, the final one that we use for our final model is called the Mishra, and we do it on 200 samples with 20 external raters. So the way a Mishra works is that there is a reference audio, which in this case is the uncompressed audio, and there are multiple codecs. The rater does not know which one is which, right? So they only see 1, 2, 3, 4. And an important thing is that we also hide the reference among the codecs. So either 1, 2, 3, or 4 is also the reference. The reason why we hide it is that it's a good way of filtering raters that didn't take the time to perform the task, because if they don't find that the reference which is hidden is as good as the reference that is not hidden, it means that they just didn't listen. So because the task that we expect from them is that they have to rate the fidelity of each codec to the reference between 0 and 100. So this slide is kind of our flagship result, I think the most impressive of the paper, because in terms of baselines, we took the most challenging we could find. So the first one is Opus. As I say, it's used virtually everywhere in the industry. And the second one is EVS and is specialized for telephony. So it's mostly specialized for speech. Lyra, as I said, is the model that was before in production at Google Duo. And so we can see that at 3 kbps, SoundStream, when it's scalable, it loses a bit of performance compared to a bitrate specific SoundStream, but it's kind of moderate. And SoundStream at 3 is much better than Lyra at 3 kbps, and even better than Opus at 12, right? So with 4 times fewer bits, we get a better reconstruction quality. At a medium bitrate, now, if Opus operates at 6 kbps, if SoundStream operates at 6 kbps, again, it's much better than EVS and Opus at the same bitrate. And now it matches Opus at 16 and EVS at 13. To give you an idea of the quality of compression, I'm going to play the same example compressed by Opus and by SoundStream at 6 kbps. So I hope that you could hear the significant difference between the two codecs. And finally, at high bitrate, SoundStream at 12 kbps matches Opus at 20. So maybe what you are noticing, that we noticed as well, is that there is diminishing returns, right? Because before we had Opus at 3 that was as good as Opus at 12, and now SoundStream at 12 is as good as Opus at 20. So we went from a factor of 4 in reduction of bitrate for equivalent quality to not even a factor of 2. And actually, if we go to even higher bitrate, SoundStream becomes less and less competitive than Opus, at least in the versions that we published. And since then, we have been working on improving the quality at high bitrate. Because, for example, for musical applications, people are expecting much higher bitrate than 12 or 20, because people want to listen to high quality much higher than speech over video conference, for example. So now, I want to mention a few ablation studies that we did and some analysis of the complexity. So we have a model that we kind of call large, but it's compared to current standard is very small, right? It's 8 million parameters, and it already runs 2 times faster than real time on a single Pixel 4 CPU. Now we can reduce by a factor of 4 the number of parameters, and this increases the real time factor to 7.5 times real time. So now what is interesting is that we observe that reducing the capacity, it was not the same to reduce the capacity on the decoder side or on the encoder side, so before quantization or after quantization. Because what we observe is that we can significantly reduce the encoder side with no loss of quality. So here you can see that we keep, the decoder remains large here. So we have a large decoder, but you're going to reduce the size of the encoder. And by doing so, we are barely reducing the audio quality as measured by VSCOL. Again, the higher is the better. However, the retime factor is going to increase from 2.4 to 18.6 for the encoder. So we get a very large speedups at a very moderate cost in performance, which is really not the case if we do it on the decoder side. So the same reduction in computation on the decoder side is going to harm the performance much more than if we did it on the encoder side. Another ablation study that we did, as I said in the beginning, a big difference with Lyra is that Lyra does not learn the encoder. It's a spectrogram, right? And unlike them, SoundStream trains the encoder, the quantizer, and the decoder in an end-to-end fashion. So to evaluate in a control setting how the end-to-end approach improves over a fixed approach, here we compare the VSCOL. So it's the same quantizer and decoder, but the encoder in one case is spectrogram, so kind of similar to Lyra, and the other case that's the convolutional encoder of SoundStream, and you can see that it works much better. As I said in the beginning also, so for a constant budget of bitrate, so here it's a 6 kbps, we can choose how we are going to split this budget among a large number of quantizers with small codebooks or fewer quantizers with large codebooks. As I said in the beginning, theoretically, the best combination would be a single quantizer with a gigantic codebook. What you can observe here is that indeed, so all of this is the same bitrate, but for example, for the same bitrate, you can use 8 quantizers with 1024 vectors, gives us a VSCOL of 4.01, or in an extreme case, 80 layers of quantization with only 2, so literally a binary tree, so only 2 vectors per quantizer, and in that case, we get a reduction in quality. What is interesting, at least in my perception when we run this experiment, is that seeing that 80 quantizers, so you really have to imagine that you are going to cascade 80 layers of quantizations that are all trained by backpropagation. It still works. So already the fact that it converges was quite a good news. And even though there is a degradation in quality, it's not that bad. What is also important to say is that when you have a lot of quantizers with small codebooks, quantization and dequantization is much faster because you basically perform 80 times a nearest neighbor search with only 2 vectors, which is much faster than having 8 nearest neighbor search among 1024. So a final application that we wanted to add, and that is kind of easy to do in a context of deep learning, is to serve compression and enhancement at the same time. So basically, the idea is that we added an extra input to SoundStream that comes either as the encoder or the decoder side, and we made it time dependent. So it's kind of a binary value that evolves a long time. And when it's 0, it means that we don't denoise. And when it's 1, it means that we denoise. So what I'm going to play is the original noisy audio. And then I will play an audio that is denoised using this mask. So 5 seconds of no denoising and 5 seconds of denoising and so on and so forth.
The Edison construction department took entire charge of the installation of the plant, and the formal opening was attended on October 1st, 1883, by Mr. Edison, who then remained a week in ceaseless study and consultation over the conditions developed by this initial 3-wire underground plant. The Edison construction department took entire charge of the installation of the plant, and the formal opening was attended on October 1st, 1883, by Mr. Edison, who then remained a week in ceaseless study and consultation over the conditions developed by this initial 3-wire.
So you could hear how when we turn on the denoising, it removes the background noise, and we can turn it back whenever we want. Another side effect of that is, imagine, for example, right now while I'm speaking in Zoom, there is a denoiser that is activated by default, right? The goal is to remove the background noise when I'm speaking. In a way, you can think that with the standard codec, the way it works is that the codec is going to encode my speech and the noise, is going to send it over the network, and then some denoising algorithm is going to decompress the audio and remove the noise. So in a way, it's kind of a waste of bits because you send a noise that you just want to remove afterwards. So what we also showed is that the nice thing with our model is that if you remove the noise before quantization, basically you can save a lot of bits that can be rather allocated to improving the speech quality. So there are savings in memory by using this on the encoder side.
Neil?
Yeah.
Question? So could you go back one step and explain a little bit more about what is the denoising? So you add noise to the input and you train it to remove this noise.
Absolutely, depending on the conditioning. So when the conditioning says no denoising, it's trained to reconstruct the same audio. And then and when the denoising is on, the model is asked to reconstruct the audio without noise. And during training, the way we can have these pairs is that we actually have clean speech to which we artificially add background noise.
Okay, thank you.
You're welcome. So to conclude, even though that's not the real conclusion because I added content, so SoundStream is the first neural audio codec that outperforms state-of-the-art production codecs with 4 times fewer bits. It can run on a single smartphone CPU in real time. That's also the first neural codec that is scalable, and so is kind of really usable in production and performs denoising on demand. So we are currently working on improving it even more. So it has been almost a year that we have, or even a year that we did this work. And since then, we have been able to reduce the complexity of SoundStream by actually several dozens of times. And so, yes, and so there has been a huge work on making it lighter and even faster because we want it to be able to run on low-end devices that don't have a lot of compute. But what I would like to finish with is rather a more exploratory follow-up work that was inspired by SoundStream and which is related to generative models. So basically, a goal in audio for the audio community is to generate high-quality audio with long-term consistency. So let's say you want to be able to generate a piece of music that is coherent across like 30 seconds or a minute, or you want to generate speech also that is consistent along several seconds and so on. So the idea that came from SoundStream and I mean that we saw in the literature is that there has been some people who have been working on doing audio generation as language modeling. Now, since then, there has been the same in image, for example, with Party, where basically you discretize a signal, whether it's an image or an audio. And then since you discretize it, you can train a language model to perform prediction, and then you can go back to the continuous domain. So what we thought is that SoundStream is kind of a good solution to that, because the big challenge is that language models, they require a finite vocabulary, right? Because you perform a classification task when you predict the next token. So typically, your tokens in NLPs are going to be the set of words in a language or the set of characters in an alphabet. In our case, we want to represent audio into a finite vocabulary. And this finite vocabulary, it can be actually the dictionary of the vector quantizer. So what I showed in the beginning is that you can take an embedding and represent it by a token which is just the index of the code words that will represent it in the dictionary. The second challenge is the long-term dependencies. As I said, SoundStream, for each second of audio, it provides between 50 and 75 frames based on the original frame rate, versus 16,000 for speech that is at 16,000 kilohertz. So if we cast audio generation as predicting SoundStream codes, we basically only need to predict 50 to 75 values a second instead of predicting 16,000. Another thing is that language models are sequential models, right? So they predict a sequence of tokens. The problem that we have is that the residual vector quantizer, it has several levels. So for example, you have 8 quantizers with 10 bits. It means that you have 8 different dictionaries or vocabularies, each of size 1024, which is 10 bits. A standard token sequence for a language model will be like token 1, then token 2, then token 3, then token 4. For example, the cat is around, right? That will be 4 words that you will represent by their index in the dictionary, and that you will flatten as a sequence. So in a way, we also need to flatten the codes of the tokens of the residual vector quantizer to be able to perform language modeling. So basically, the way we do it is that we simply flatten based first on the quantizer index. So let's say we have a time step, which is called token 1. We are going to encode it through the 8 different quantizers, and it's going to correspond to 8 tokens. So the first level of token 1, then the second level of token 1, the third level, and so on and so forth. And then when we have reached the 8 levels, we go to the second time step. So there is a clear limitation to that, is that let's say you have 8 quantizers, going to multiply your sequence length by a factor of 8, which is pretty expensive with self-attention. But there are some solutions to that that allow to model long context. So to summarize, the way it works is that if you want to do a generative task, let's say you have an input audio and you have a target audio. And in the demos I will show, the input audio is simply, for example, a piece of speech. So we take 10 seconds of speech and we feed, for example, 3 to the model, and we ask the model to predict the 7 others. So it's really like you will train a language model to predict the next word based on the previous one, and then you can sample random text. You train on Shakespeare, you can sample a Shakespeare-like text. In the same way, we can train a model and generate audio afterwards based on it by sampling random sequences that will be different all the time. We take this audio, we pass it through the SoundStream encoder, the quantizer, a language model produces the next tokens, they are passed through the SoundStream decoder and reconstruct audio. So a first application to that has been published at ICML 2022 with colleagues at DeepMind and Google. And what we did is that we encoded a piano dataset called Maestro, which is 250 hours into SoundStream tokens. And we trained the language model for next token prediction. And then we reconstruct audio. So you're going to see the quality here. So it's not bad, right? At least it sounds good, thanks to the SoundStream tokens. However, the structure is kind of lacking. It's a bit chaotic, right? So since then, we made a second paper that I'm very proud of. We put it on archive this morning, actually. And it's called AudioLM. And basically, based on these intuitions, we spent a lot of time trying to find the best generative model we could that could generate in the discrete space. And I won't have time to go into details. I really recommend you check the paper. But basically, what you listened before, as I said, it had high quality that comes from the high quality of SoundStream. But the sequence modeling of the tokens was pretty poor in a way. So there is a lack of structure and of temporal consistency. AudioLM combines SoundStream with another tokenizer that was previously proposed. We also scaled the training data. So for example, for piano, we went from 250 hours to 40,000 hours of piano performances. And the results that you're going to hear, basically, you're going to hear a demo for speech continuation and one for piano continuation. So again, the way these models were trained, in one case, it's on speech, and in one case, it's on piano, but it's always the same task, is that the model is asked to predict the next SoundStream tokens based on the past one, and then we can give it a prompt, in that case of 3 seconds, and the model has to generate the rest. What you're going to see is that for speech, it's almost indistinguishable than if it was real speech, and same for piano.
Nay, nay, lording, answered Wolf, we know not how to call you lord or lady. We have lived too long in the forest, and are now
And again, very important to emphasize, the speech model has never seen a single character of text. It's trained only on audio, right? So it just listened to people speaking and was able to learn the syntax, the lexicon, and the semantics of human language. And the same for the piano. It has never seen a partition or a MIDI. It has only listened to performances. And it's able, if you give it a 3 seconds of a piano performance, it's able to generate a continuation that has the same recording conditions, the same timbre, and for speaker, for speech, the same. It's the same speaker ID, same reverberation, same noising condition, and so on. So I really recommend you take a look at this paper. It was not included originally in the topic of the talk, but since it's a very exciting results and really a work that was inspired by SoundStream, I really wanted to share that with you today. So thank you a lot for your attention. Now, if you have questions, I will be happy to answer them.
Thank you, Neil, for the talk. Do we have some questions? Perhaps I can start with one. So in both the encoder and the decoder in SoundStream, you have sort of regular convnets, 1D convnets. Did you consider any other architectures such as WaveNet?
So if by WaveNet you mean using dilated convolutions, we have some layers of convolutions that are dilated, which allows scaling a lot the receptive field.
Okay.
However, the big difference is that WaveNet, it's an autoregressive model, right? So WaveNet at inference, you need to generate 16,000 values in a sequential fashion per second. So that's why the original WaveNet took, I think, something like 1 or 2 hours to generate a few seconds of speech. In our case, we want to operate in real time. So there is no autoregressive component. It's really a parallel convnet. And the way it reaches the quality is thanks to the discriminator loss. If you train it only for reconstruction, so without the adversarial training, it sounds okay, but you have a lot of artifacts. If you train it with the discriminator, it sounds as good or maybe even better than WaveNet, but it's parallel. So that's what allows us to run in real time.
Mm-hmm. Cool. Do we have some more questions from the audience?
There is a question in the chat. The generated speech in the AudioLM example, was it close to something the training set or new text? So first of all, it's from a new speaker, right? And you can see in the demo on the paper, the way we observe that it does not come from the training set is that regarding the text, maybe there are some bits that come from it, but we take a single prompt of, let's say, 3 seconds, and we generate a lot of continuations from it. And you see that they are all different, yet they all make sense based on the original prompt. And what is clear is that there is absolutely no overlap between the speakers seen during training and the speakers seen during evaluation. So the fact that AudioLM is able to replicate the voice of a new speaker that was not seen during training shows that it can generalize, at least in terms of speaker identity.
I have a question, Olaf.
Yes.
Yeah. Why do you think the codec is so much more efficient than the previous ones? I mean, there are a few parts of that. Where do you think the most improvement happens?
So I think what is having access to a lot of the training. So there is the training data. There was a lot of iterations on the loss function and on the architecture, in particular when you work with a constrained amount of compute. What I need to say, because it's very important, is we are, even though SoundStream was already pretty efficient and is now very fast, it's still not competitive in terms of speed with Opus. To give you an idea, Opus is something like, it's almost 100 times real time. So it's extremely fast. So one thing is that Opus, for example, and I don't know the details of why, but below 9 kbps is going to reduce the bandwidth, and so it's going to have a drastic drop in quality. SoundStream, we can train it to be very good at bitrates that are lower than 9 kbps. And in that case, what we are trying kind of to justify is that even though we are still not competitive in terms of speed, the gain in quality is so important that it's worth spending more compute. So to answer more precisely to the question of what was the key component, The ablation studies show, first of all, that training end-to-end is better than training just a part of the model. That's one of the ablation I showed. We didn't even put it in the paper, but adversarial training is critical. Otherwise, just the quality is too bad. And the architecture choices also, but there are so many that it's hard to do an exhaustive ablation between the activation function, the number of layers, and so on and so forth. But the most fundamental difference with Opus is adversarial training and large data.
I actually meant where in the architecture compared to the hard-coded codecs it happened. But are there any reference to the paper in the call in the invitation of which you sent?
I'm not sure. But
Neil showed a few papers, a few references into the paper, but
absolutely. Okay, if what I can do is I can send the different papers mentioned here to Olaf after the meeting.
Yeah.
Yeah. Yeah. And in terms of so for specifically the architecture, so the big difference is that in the case, and for me, that's the question of optimality, right? So you take a high pass filter, is going to be designed to be good, but it's very different to optimize by propagation, by gradient descent a filter to be really optimal, and optimizing the values by human iteration, right, by hand. So I think that gradient descent is just a super efficient way of finding non-obvious and very good solutions that are probably more challenging to find by human iteration. At least that's my take.
I put links to SoundStream and AudioLM in the chat for everyone.
Thank you, Neil.
Thanks, Mikhail.
And Thomas put a link to the Hawthorne paper.
What is the current memory usage of the model? In what sense? In the sense of the RAM or in the sense of storing the model? The model is, in total, it's a few megabytes in total. In terms of memory usage, it's hard to tell, but we are able to run it on very low-end smartphones now. Basically, smartphones that are many years old. So.
Maybe you went through it in the beginning. I missed the start where you showed the architecture of the SoundStream one. But what's the? Maybe you can go through a little bit. What's the difference between, let's say, WAV2Vec 2.0, because that also has this quantizer unit as well, right? But it's a transformer network initially.
Yeah. So let's go. Wait, where did I put it? Sorry, I forgot. Yeah. Okay, so there are two main differences with WAV2Vec 2.0. So WAV2Vec 2.0, it's as you say, it combines convolutional layers and self-attention layers over a context that is much larger. I think something like 1 minute or something like that. So computationally, it's impossible to expect to run that real time, even on an accelerator. So like a GPU or TPU. So on CPU, you can forget it. But I think the main difference is fundamentally the goal of WAV2Vec is that is discriminative tasks, right? So you want to pre-train a system to learn representation that you can then fine-tune to do speech recognition or audio classification. So even though you're going to quantize activations of your transformer, these representations, they are not meant to be invertible because they are just used as pre-training, and then you're going to predict characters or class labels from it. So they don't need to encode the fine acoustic details. And that's the whole point of AudioLM. We observe that SoundStream on the other end is really trained to encode every fine detail of the acoustics. But on the other end, we found it, and that was the demo of Perseveria, it was pretty challenging to have good sequence modeling. WAV2Vec tokens, that's the other way around. They are not invertible. So if you try reconstructing audio from it, the quality is crap. However, they are excellent at modeling high-level information. So AudioLM is basically combining WAV2Vec tokens and SoundStream tokens, concatenating them, predicting first the WAV2Vec, then SoundStream, and you get high quality audio and long-term structure.
Okay, all right, thank you.
You're welcome. And there is a question in the chat by Felix, but I think it was a direct message, but I read it because I think it's interesting for everyone. Does the model recognize different accents? Some accents or languages have click sounds that sound like noise. So all of that depends on the training data. So I did not mention it, but we train the model on a mixture of music, speech, and noise, so that it's very good at reconstructing pretty much everything. But this has a cost, right? Because as I said, it's a feature and a bug in a way that it's universal, but then it's less specific. So we also have versions. For example, we work with the Magenta team inside Google that is focusing on music generation. So we have trained SoundStream codecs for them that are specifically dedicated to music. And by focusing on music, they work better on music than if they try to be universal. The same for lungs with click sounds like Chichonga and so on. If you have a data set that represents this kind of sounds and speech production, and you train the model on it, there is no assumption in the model that will make it not work on this kind of data, because there is no specific assumption in the model regarding the frequency content or the type of formants or phonetic content, or even whether it's phonemes or any noise. So yeah, if you have the right training data, you will have a good model.
All right. That's perhaps the last question today.
I have one more if there's time. You didn't say so much about the exact learning process inside the quantization step. Is that the same as in VQVAE?
Exactly. It's the same as VQVAE 2, actually. So it's the version with exponential moving average instead of stop gradient and iterative optimization. The main difference with VQVAE 2, when I say that we didn't invent residual vector quantization, we didn't also invent VQVAE. What we did is basically residual VQVAE. That's really exactly that. It's every quantizer is exactly VQVAE.
Okay, thank you.
You're welcome.
Do we have some last questions? Otherwise, thank you very much, Neil, for this talk.
Thanks for having me.
And next week we meet again, and we'll have Martin Hellqvist, who is at Uppsala University. He's going to talk about a work called Fake It Until You Make It. Fake features can improve estimation performance. So that's certainly going to be an interesting talk. Welcome back next week.
Thank you. Goodbye.
Thank you. Bye-bye.